Hello, this is Aslan. I'm back again with a new project on modeling isothermal hot deformation behavior of any metal or alloy using a numerical approach based on VUHARD subroutine. So the idea is basically this is a reference paper that I'm using, and this is also a second reference paper that can be used to study the model. So basically, we all know that metal and alloy at high temperature experience some sort of strain softening as well as temperature softening. So in order to model this temperature softening and strain rate softening, there is a model which we usually call as strain-compensated Arrhenius model. So this model is basically used to model the hot deformation behavior for any metal and alloy based on strain compensation method. In this study, first of all, we need to investigate, and experimentally this can be modeled using a Gleeble 1500D thermo-mechanical simulator. And in ABAQUS, or through numerical simulation, we have used a VUHARD subroutine, which is based, and the detail of this VUHARD subroutine is as follow. First of all, we all know that this material experience certain sort of deformation at high behavior, at a certain sort of softening at high temperature. So you need to model the flow stress behavior at high temperature. You can see over here the two stress and strain curves, and we can see that at the higher as the strain increase, we experience the softening behavior. So this softening cannot be captured using conventional model in ABAQUS. So that's why we need some sort of model, whether it is a Johnson Cook type. We need to modify it, and we can use strain-compensated Arrhenius model, which is already a validated model for modeling hot deformation behavior. So in this case, in order to validate the study, first of all, we have made an Excel sheet. In Excel sheet, we have entered all the formulas for the modeling. We have to enter the value of these formulas all depend on the strain. So it's a strain compensated model. So we need to measure these parameters, these all parameters individually for different strain, and then check the flow stress behavior. So this is what they have done. So they have, in the next stage, you can see that this is basically Arrhenius model, and in Arrhenius model you have to find the value of all of parameters like log of strain rate simply as a function of stress, so as a function of stress, similarly you can see over here, yes, these parameters, sorry, n as a function of true strain, similarly alpha as a function of true strain, similarly q as a function of true strain, and ln a for as a function of true strain. So based on all for different strain, we have to capture, we have to follow, we have to understand these parameters as the function of strain, and then we can put it in the formula, which is over there, over here, this one, this formula over here, and then you can find the flow stress behavior based on function. Numerically, we need to check this using we have done it using a model which for a different strain rate. So you can see over here we have a cylinder which we can overhead, which is normal cylinder, and there these, and these cylinder is supported in place by two plates. The bottom plate is fixed, and through upper plate we apply the top displacement, the bottom displacement, and you can see over here. So you can see the localized flow stress behavior as the cylinder is compressed. So you can see that, as you can see in the center, that there is a high flow of material, and the flow is localized at the center as a result of compensation. So this also can help us to identify the dynamic recrystallization, which is the formation of new grains, and also in order to in case of any deformation, if you want isothermal deformation, if you want to identify the area having a high flow of material, which is very crucial for a material design, so we can follow this subroutine. So in the same case, what we have done, we have applied the displacement over here, and you can see as the material is increasing, you can see the formation of flow stress in the center, and as the material is fully compressed, you can see over here, we can see the high flow of material in the center. So this is basically the flow localization. So the top edges at the corner and the center experience a high flow of material. So that's why we can see the flow localization behavior inside the center. Similarly, for the uh, in the next stage we can see over here. uh, Yes, in the paper we can see. Yes, now for the subroutine, and we can try this at for a different strain. And in the subroutine, how the procedure for UHARD and VUHARD is same. Just we need to integrate in order for Arrhenius compensated model. Both in UHARD and VUHARD subroutine, we have to differentiate the stress or flow stress as a function of strain. First we need to integrate them. We need to differentiate with respect to strain, and the second we need to and in the third portion we need to differentiate it with respect to temperature in order to compensate, in order to induce the temperature dependent softening. So equation 16 is basically strain rate softening, and equation 17 is basically the strain the temperature based softening. So how it has been done, you can see over here. This is the Arrhenius subroutine. This is its interface, and then you need to differentiate with respect to stress, with respect to strain, and with respect to strain rate, and then with respect to temperature. So in this subroutine, you will differentiate all of these parameters with respect to as given. So they have done it using the UHARD, and we have done it using VUHARD subroutine. Both yield the same results, just the numerical process for this is different. In the next stage you can also model the dynamic recrystallization, which is the formation of new grains. So we can see that at the center of localization, this dynamic recrystallization, it is also mentioned somewhere in the article. And so in the next article, you can see that for the dynamic recrystallization, we another subroutine which we call as VUSDFLD, like the user-defined variable are defined, and in this subroutine, this dynamic recrystallization is defined in term of critical strain, the strain net for softening, and which is and the two other parameters K and N, which are the material parameters. And you can see it for a different alloy, for a different metal alloy, the formula is different, and it all depend on your value of critical strain and the material parameter K and N. So in the subroutine you can also see there is a the solution dependent variable 3, which you can give an us idea of solution dependent variable inside this uh, um, inside this material, or inside this component. So that's all for this video, and if you want this video, you can simply visit. If you are interested in this project, just visit arsalanmaa.com, and then after visiting, just click on design simulation project, and you will find it in the drop down list of the project. You will find it in the drop down list of the project. And if you want to contact me, just click on a contact. Just enter your name, uh, email, and the specific idea of the project. So for this project, the fees is $500, and this project for the project you can just write me modeling isothermal deformation, and I will share the file isothermal deformation. So that's of metal and alloys, and you can just send it to me 16 and just submit, and I will get it, and I will share the further details with you that how you can get the files for this model. So that's all from me, and I hope I can come next with some more exciting projects. Many thanks. Keep supporting.